Now let us look at the correctness of the method Nelson-Oppen. So we have noticed if there are no quantifiers, variables behave like constants. In the lecture, we will refer models and assignments together as models. And remember that in our model of FOL, you have functions, predicates, and some variables, and they are given models. And in the case of variables, you give them assignments. However, since our formulas are quantifier free, we can treat them uniformly and call everything as models. Now let us define a projection function, which is this guy. And what does it do? If you have defined values for s and v function symbols or variables, then you can project on a subset such that you only define for some smaller set of variables and function symbols and predicates. So now let us define something called homomorphism and isomorphism. It relates to models. If I give you model M1 and M2, and we can say that they are behaving in a similar way if the following holds. If there is a homomorphism between them. So if there are two models M and M prime and assigning values to one signature S and some variables V, and then we have models which assign values to signature S and variables V. So if we take a function in from our signature and apply it on values d1 to dn coming from the state space of model M, and then we apply the model of function f, and then whatever we get, we apply my homomorphism function h, which takes me from the space of M to space of M prime, and we get a value. And we apply the process other way around. First we take my elements in M space and bring them to M prime space, and then apply the model of f in M prime space, and we get a value in the M prime space. So this also produces a value in M prime space, this also produces M prime space. And if they are equal always, then somehow the homomorphism function is giving me the evidence that function f behaves exactly the same way as it behaves in model M and M prime. Similarly, we can do for the predicates. The behavior of exactly same set of tuples which are related by h are satisfied in M and M prime. Similarly, we can relate the valuation of the variables. A homomorphism is called isomorphism if MH is 1 to 1. Okay, so if there are no like many one situation, if like two different points in one space going into one point, this is not allowed. Okay, then we call it isomorphism, and it's called isomorphic if H exists that is also onto. Okay, so it covers everything. Okay, so it's not the case that some things are left behind. So that is called isomorphic.
Now we will look at a series of theorems. They will successively prove that that if you solve formula F1 and F2 and get the models, how you can stitch them together to obtain a model for the F1 and F2. Modulo, you have certain conditions as such. Okay? So first thing, let's look at if you have M1 projected on the common variables and M2 also projected on the common variables, if they are isomorphic, then this guy is satisfiable if and only if. Okay, so how that is happening? Okay? So if let's suppose this is satisfiable, then you can choose a model, project on the variables of S1 and the variables of S2, and then you get the models for F1 and F2, and then you are done. So that's trivial. In the reverse direction, you have models F1 and F2, models F1 and M2, and you want to compute a model M for F1 and F2. So what you need to do is that somehow you need to do the stitching of these two models. So let H be this isomorphic function. So let's see how we build the M. Let domain of M be the domain of M1. You just pick the one guy and call it the domain. all the symbols and variables occurring in the formula F1 get the same model from M1. If any variable that occurs in V2 but does not occur in V1, what you do, you pick their value that is assigned by M2, apply this inverse of homomorphism, and then you get a value in the model M for the variable V. For the function f that does not occur in S1 but occurs in S2, you do the same thing. You just you using the homomorphism H, you construct the model for M. That's basically taking the reverse map. Okay, so you basically say what is the behavior in M2, some set of points it is taking somewhere else from H, you map it back, and you say, okay, where was this point was mapped, and exactly that will be the model of the F, okay, in the model M. Or similarly, you do the predicates. It's very trivial to say once you do this kind of homomorphism mapping, the formula, the models remain satisfiable for the F2 also. So therefore, F1 is F1 and F2 satisfiable. So next, we need to ask ourselves this question: is that what more we need to do to show that F1 and F2 is satisfiable if and only if M1 satisfies F1, M2 satisfies F2, but isomorphism was too much too semantic condition. You cannot really check that. So what do you need? Okay, so if we have a same size of the models and all the common variables which are occurring there, the xm1 is equals to ym1 if and only if xm2 is equal to ym2. Okay, if that condition holds, then we have a equivalence and satisfiability. That means again, if you have these conditions there, then you can get a built and satisfying assignment for this formula. How do we do that? Okay, the forward direction is again trivial, and then let's look at the reverse direction. Let's Vm be a set where V is a variable which is occurring in set V, and see what value is assigned in M for that variable, and then you say that Vm is that set. Okay, so now let's construct a edge as follows, which maps all the variables that are all the values that are assigned in M1 and all the values that are assigned in M2. Okay, so essentially just pick the value that was assigned in M1, map it to the assigned value in M2, and for each V1 intersection V2. Okay. So we will define H is well defined because of this property, and 1 to 1 and on to. We can check that this because of this property this holds. So therefore, this size of these sets V1 intersection V2 M1 and V1 intersection V2 at M2 is same. Therefore, if you remove this set from dm1 and dm2, then again their size is same, because I have dm1 and dm2, their sizes are same, right? That was part of the assumption. Now we can extend h. H was working at this set, right? Now what we can do, extend h to this sets, okay, right? H was mapping this set to this set. Now we can extend h to h prime, which is start mapping all the other elements, okay. So we have this big set m1, okay, and the big set m2, and there is some small set which we had constructed h, right? So now what we can do, we can extend it for all the values, and since sizes are same, then you can always construct such an h prime. By construction h prime is have homomorphism from m1 to b1 intersection b2 to m2 b1 intersection b2. Therefore, by previous theorem, f1 and f2 is satisfiable. Now we continue. if we have a Ti as a stably infinite SI theory, and Fi and Si be a formula with variables Vi, and let S1 intersection S2 is empty. Signatures have no common symbols, right? And you have F1 and F2 is in this theory, and there is an equivalence relation V1 intersection V2 such that Fi intersection with F, that equivalence relation, is Ti satisfiable. But forward is again trivial. Reverse direction again is very not difficult to see how it connects to the previous theorem. Suppose there is an equivalence, okay, V1 equals intersection V2 such that this is Fi and F tilde is Ti satisfiable. Then we have Ti, and since Ti is stable is infinite, there's an infinite model Mi, okay, that satisfies this formula. So due to LST theorem, which is a very standard theorem, it says that if you can construct infinite models of two different formulas, then you can construct infinite models of some size, let's say countable size. Let's say a countable size you choose, then M1 M2 can be countably large. Now their sizes are same, and M1 satisfies F tilde, M2 satisfies F tilde. So therefore we have this property that if xm1 equals to ym1, then if and only if xm2 equals to ym2, but such that v1 xy is element of this informal symbols. So therefore the right hand side of the previous theorem holds. Therefore we have the f1 and f2 is satisfied. Therefore we have a Nelson-Oppen procedure in our hands.